Hi! Today we are continuing where we left off with in our previous Further Maths tutorial video, where we introduced series formula as a topic, introducing the formulas themselves, and now today we're going to be getting on with actually answering a question itself. Specifically, what we're looking at in this topic is formulas that help us work out the series for things that have a polynomial nth term. Except often we're not writing the nth term part in terms of n, we're writing it in terms of r. So I guess we should call it the rth term. Anyway, hopefully you know what I mean. So key facts before we continue. The first of which is formulas. You need to know the series formulas for the sum from 1 to n for 1, for r squared, and r cubed. I was feeling lazy and couldn't be bothered to write those formulas on this slide, but worth pointing out right now on the screen there should be appearing a link to the previous video where I did show what all the formulas were as well as where they came from. So if you haven't already, check that video out. But also because we're going to be going through examples, you'll see me use all the formulas anyway as part of those examples. So even in this video, you'll get to see the formulas one way or another. Another key fact that's going to be really helpful and useful is, basically, if you have a coefficient in front of any of the algebra inside the nth term part of our series, then you can factor that out the front in front of the sigma notation. So an example for that would be to say if we are finding the sum from r equals 1 to n for 5r squared, we can see there's that coefficient of 5, and then we can move that out the front of everything. To make it easy. The reason we do that is because then we know we can just sub in the formula for the sum from r equals 1 to n of r squared. And then there's another key skill we can use, which is that if you see plus or minus symbols in between our terms of our nth term for the series, you can use them to split up the series into bite-sized chunks that are then easier to substitute stuff in for and calculate. So for instance, if we have the sum from r equals 1 to n of 3r squared minus 6r plus 2, you might be looking at it going, oh my goodness, that looks a bit hench. And what we can do instead is we can then split that up into 3 individual series. A series for 3r squared, take away the series for 6r, and plus the series for 2. Minus and plus decided by whether there was a minus or plus in the original nth term. But then you don't have to just stop there. You could then combine this fact with the previous fact we said, which is moving coefficients out the front. So the 3 in front of the r squared can be moved out the front there. The 6 in front of the r can be moved out the front of that series. And then it's a bit weird, but we can split the 2 up as 2 times the sum of, or series I should say, of 1 from r equals 1 to n. And the reason we do that is just because, again, there's a formula for specifically the series for 1. Okay, and then the final hint I'm going to give you before we get into examples is to say, although there's a big temptation once we've substituted all the algebra in to just start multiplying out brackets and doing that sort of stuff, don't do that immediately. Instead, always look to try and factorize out any common terms out of everything, because otherwise you're going to end up with massive polynomials as your answer, which is not going to be very nice to try and simplify. So always try to factorize stuff out first. Okay, let's look at our first example. So we need to find a fully factorized expression for this series. The first thing you do is do what we were saying in the previous slides, which is to effectively split this up into the individual series. We can view this as 12 lots of the series for r squared from r equals 1 to n, minus 8 lots of the series for r from r equals 1 to n, and then plus 5 lots of the series for 1 from r equals 1 to n. And that's useful because then you can substitute in the various formulas for those things. We're going to have 1/6 lot of n plus 1, 2n plus 1 for the formula for r squared. Remember, that's one of the ones that's in the formula booklet. Then take away 8 lots of the sum of, well, not the sum of, this is the sum, the formula for it, half lots of n plus 1. Remember, the sum of r is one of the formulas you need to remember off by heart. So that's one I got from memory. And then lastly, the sum of 1, but we've got 5 lots of it. The sum of 1 is just simply n. Although that's very simple, you do have to remember it again as well. Cool. So the rest of this question is just going to be us simplifying and then factorizing. Conveniently, you can see the 12 and the 6 are going to become a nice 2. And then we've got the other stuff still there. We've got the 8 and the a half combining to give us 4, or minus 4 I should say, to be exact. Let's keep that inside there. Unnecessary brackets, but oh well. And then plus the 5n. Now, this is the point I was trying to make before. It's very tempting this stage to maybe start looking at this stuff and go, oh, I can start multiplying out brackets. But no, that's unnecessary. Before we do that, we can see that every single term in this expression has an n. So let's start by just factorizing n out of that entire thing. So if we do that, we're going to have n, and then that will leave us with 2 lots of n plus 1, 2n plus 1. We're going to have minus 4 lots of just n plus 1 because we've already factorized the n out of it. And then lastly, we've got just plus 5 because we've factorized the n out of that too. Now see, the advantage of having done this is it now means, although I still do have some brackets to multiply out, the most I'm going to have to multiply out is getting stuff that involve a quadratic. And that's a lot nicer to deal with. We can deal with quadratics. We can factorize them if needs be. But if it's a cubic, that suddenly instantly becomes a lot more of a pain to do. So proceeding with that, don't skip steps. That's where people make silly mistakes. So, individually first multiply out the brackets there. So 2n plus n plus 1. We're going to have minus 4n minus 4 plus 5. Then we could do some more stuff. So we could times by the 2 and gather the 2n plus n. So therefore we're going to have, what are we going to have? We're going to have 4n squared. It was a 3n, but now times by 2 to get 6n. Plus 1 times by 2 is 2. Minus 4n minus 4 plus 5. We've got the n out the front still, and then we can make the quadratic in its final simplest form. So 4n squared plus 2n, and then we have a 2 minus a 4 plus a 5 is a plus 3. Oops, if I can write a plus 3. There. And then once we have that, then it's worth pointing out that you would then try and factorize the quadratic that we've got there, if you can do that. Now, funny enough, in this particular case, this is a quadratic that doesn't factorize. So actually, in this case, we've reached the final answer. That is it in fully factorized form, but sometimes you can factorize it more because the quadratic you have is a bit more nice. But there you go. And on to the next example, example 2. Again, we want to find an expression for this and give our answer in fully factorized form. I haven't written that wording here. They would have that wording normally if they wanted you to. I've just got rid of it to provide more room on the screen for me to do my working. Okay, and also to save a bit of room, I'm going to skip that very first step we did last time of literally showing myself manually splitting up the series and factorizing the numbers, the coefficients I should say, out the front, because you don't need to show that, but it's just something that helps you see what's going on. So jumping straight to dealing with the formulas, we have the sum of r cubed, and that's one of the ones from the formula booklet. So we're going to have a quarter n squared n plus 1 all squared. We're going to have 3 lots of the formula for the sum of r squared, so that's going to be 3 lots of 1/6. So we could write that as 3/6. N plus 1, 2n plus 1. And then we're taking away 19 lots of the sum of r, so that's 19 over 2 n plus 1. Again, reminding you that's the formula you need to know off by heart. Cool. And as I said last time, although it might be tempting to multiply the brackets, you can probably start to see why that's a bad idea. If I was doing that here, I'd end up with a quartic. Oh, that'd be way too much that I'd have to deal with. So it really, really is definitely 100% a good idea to start factorizing stuff out. However, before I was just factorizing algebra. But there'll be times in things like this one where you also want to be factorizing the numbers out. Factorizing out having to deal with the fractions that we've got. Now, to see what the best fraction is, ultimately you want to simplify the fractions first and then see if you can create a common denominator. Now it's worth pointing out 3/6 is just 1/2, so I've got quarters and halves, therefore a common denominator could be 1/4. So I'm going to factorize 1/4 out of the front of the entire thing. I'm also going to factorize out an n, because all of the terms have an n, and then all the terms also have an n plus 1. So that's what we're going to factorize out of everything here. Okay, so out of that first term, we've factorized the quarter, so we're not left with a coefficient. We've factorized out n to the power of 1, leaving us with another n to the power of 1. We've got an n plus 1 squared, so that leaves us with just an n plus 1 to the power of 1. So that first term has already become a lot nicer. 3/6 we said was 1/2, but that is the same as 2/4 if we're creating common denominators. So therefore the coefficient for the second term is going to be 2. We've factorized the n and the n plus 1 out of it, so that leaves us with just a 2n plus 1. And then on the end, it was 19/2, but 19/2 is of course the same as 38/4, creating a common denominator of 4. So therefore we're taking away 38, and then actually we've got nothing else left to multiply it by because we've factorized the n and the n plus 1 out of that. Cool. Proceeding on, we're going to leave the quarter, the n and the n plus 1 out the front, and then we're going to start multiplying the brackets, the stuff that's left over on the inside, because now, as you can see, it's just going to be something fairly nice to deal with in comparison to what we're having to deal with before. So multiplying all those brackets, we get this. And then simplifying, that will leave us with the quadratic n squared. We'll have a plus 5n, and then we'll have a minus 36. So this time we aren't going to leave it just like this, because now, this time, the quadratic we have been left with is one that can then factorize further. So if we can factorize it, do it. So in this case, that would factorize to n plus 9 and n minus 4. And so there you go. That is this series written in a formula that's in its fully factorized form. Brilliant. All good so far, hopefully. I've got one more example to show you, though, of something else they can ask. And it is this thing here. So it says, show that this particular series becomes a quarter n, n minus 1, and then we've got a quadratic with an a, b, and c coefficient, and we have to find what the values of those coefficients are. To save room, I am now going to remove that wording, because now we've seen what it is, but that'll leave us more room to actually solve the question. Things to be aware of. This question is a bit more meaning. You'll see why when we start off with. Until now, I've been making the point of always factorize everything you can out the front, and that's because often that will just leave you something really nice like a quadratic. However, that won't always happen, as you'll see with this one. Sometimes you might still be, even after doing all the factorize you can, be still left with a cubic that you have to deal with. Worth mentioning that probably, not guaranteed, but probably one or two things will happen. Most of the time that will either mean you are going to have a cubic that doesn't have a constant term on the end, so therefore it's easy to factorize because then you've got another n you can factorize out the whole thing. So I'm talking about if you had something, let's say like a cubic that ended up being something like this. As there's an n that factorizes, out of all of that, then therefore you could rewrite that as that. And so then you're still in the same position we were before, where it's something that's easy to factorize. But then the other situation you can get, like the one we have here, is one where it'll be a cubic. It won't be a particularly nice one, but we're kind of already told, spoiler alert, what one of the factors of that cubic is going to be. And so therefore you can use other skills from Maths A level, like algebra division, to be able to split up that cubic and find what it fully factorizes to. Brilliant. So with all that said, let's get on with the question. So first of all, we need to write our series using the formulas from obviously previously. So the sum from r equals 1 to n of r cubed plus 3 over 2r minus 5 over 2 is going to be the formula for r cubed, which is 1/4 n squared n plus 1 all squared, plus 3 over 2 lots of 1/2 lots of n plus 1, and then minus 5 over 2 n. Cool. Nice. So straight away we can factorize a number out the front of it all because we got 1/4 of the first term. 3 over 2 and 1/2 will make another 3/4, so that's something in terms of quarters again. And then 5 over 2. Okay, that's not quarters, but you can rewrite 5 over 2, of course, as 10 over 4. So again, you can probably hopefully see why it's easy to factorize a quarter out of that. So therefore, doing that, that will be the quarter out the front there. We can also factorize an n out of everything. But unfortunately, that's all we can factorize. Although we've got an n plus 1 for the other two terms, we don't for the third term. So frustratingly, that is it for the moment. So that will leave us with an n plus 1 squared for the first term. For the second term, it was 3/4, but we factorized the quarter part out. So that leaves us with plus 3, and then an n plus 1. And then we have just minus 10, because it was 10 over 4 when we made the common denominator, and we've factorized the n out as well as the quarter. So there you go. Now we are left with something, although it's not very nice, although it's going to be cubic, we are going to just have to multiply the brackets out. So let's get going with that. We're going to end up with an n lot of n squared plus 2n plus 1 plus 3n plus 3 minus 10. Then going a bit further on with that, we're going to end up with, 1/4 n. Then multiply out those brackets, we're going to end up with n cubed plus 2n squared plus n plus 3n plus 3 minus 10. We can then now finally fully simplify that cubic. So we'll end up with an n cubed, we'll end up with a 2n squared, a plus 4n, a minus 7 on the end. Okay then, and moving what we had up higher onto the page, so we've got more room, we now need to basically factorize this cubic, which would be a bit of a pain to do were it not for the fact we're told effectively in the question that n minus 1 is a factor of this cubic. Also worth pointing out, we've got the quarter n out the front that we were expecting. Forgot to mention that before. So all we've got left to do is find what the quadratic is that we'll be left with after we divide by n minus 1. So to do that, we're going to do a bit of algebra division. In this particular case, I'm going to do algebra long division, but of course you can use the grid method, for which there is a video on my channel showing. So by all means, have a look at that video if you want to know how to use that alternate method. So therefore, for this question, we got n cubed divided by n is n squared. N squared times by n is n cubed, times by minus 1 is minus n squared. Subtract all that from the stuff above will mean we end up with 2 minus 1 lot of n squared, which will be 3n squared, and then we still have the 4n and the minus 7. Then dividing that by n squared, we're going to end up, 3n squared divided by n is positive 3n. 3n times by n is 3n squared. 3n times by minus 1 is minus 3n. Subtracting that will get us 4n minus 3n, which is 7n. And then we have the minus 7. 7n divided by n is positive 7. And then just to check, 7 times by n is 7n, and 7 times by minus 1 is minus 7. Subtract it, and woohoo, because it's come to 0, which means it did end up factorizing nicely. So therefore, what does that tell us? It tells us that our cubic factorizes to a quarter n, n minus 1, and then the quadratic we're left with is n squared plus 3n plus 7. So there you go. That was a bit more of a mean question because of all this extra stuff we had to do, the fact we were given a cubic, but that's why they made it to show that question in the original question. So therefore, by the way, should have a conclusion, and I can just put as required because it's fairly clear what the answer is. Though it's worth pointing out sometimes, depending on the wording of the question, you might want to explicitly point out what the value of A, B, and C are to make sure you get all the marks in those sort of questions that are structured like this. Cool, okay, there we go. That is all for today. We've got one more video in this topic though, because so far, the series we dealt with in this video all started at r equals 1 and finished at n, but they won't always do that in exam questions. So we'll look at some exam questions that deal with those sort of questions in the next video. Bye!